Hello, this is Professor Kuehn, and welcome back to my lectures on space, time, and motion, where we are talking about Einstein's theory of special relativity. In my last lecture, I introduced the principle of relativity, or to put it colloquially, you can't tell if you're really in motion or really sitting still. At the end of the last lecture, I promised that I would talk about a paradox that arises when considering two inertial observers who are not in the same inertial frame of reference. Remember what an inertial observer is. It's an observer who is not accelerating. That is one who's moving at a constant velocity. So again, I want you to consider two observers who are each themselves inertial observers, but are not in the same inertial reference frame. This will become more clear as I explain this. So here's what I want to do. I want you to think about a man riding on a spaceship, and this is going to be a very boxy looking spaceship because there's no sense in me spending all kinds of time drawing a fancy spaceship. Let's say we have a person in the spaceship, and then we have another person who's outside of the spaceship watching the spaceship fly by. So this is an astronaut, okay, so he's got on his spacesuit like this. And this observer, let's call him John, and let's suppose we have Luke who is riding in this spaceship. And let's suppose that John is floating out here in outer space. So here's some stars like this. And the spaceship is flying past John at some speed u. I don't know, maybe this is something like 1,000 miles an hour or some high speed. Okay? Now, let's suppose that Luke, who's riding in this spaceship, is holding on to a baseball. And Luke throws the baseball, and when he releases it, it's moving at a constant speed with respect to him, a speed v. Maybe he throws it at, 40 miles per hour. So v is the velocity of the baseball, and u is the velocity of the spaceship compared to John. Now, here is the question I want to ask. If this spaceship had a big glass window on the side so that John could see everything that's going on inside of the spaceship without any problem as it's flying past, what would be the speed of this baseball as reported by John? Okay, so let's first ask, what's the speed according to Luke? So according to Luke, the speed of the baseball is just v. That's the speed of the ball compared to Luke. That's the speed at which he measures it moving away from him. But now what is the speed according to John? Well, according to John, the speed of the baseball is going to be, I'll call that capital V. That's the speed that he sees the ball moving at. And you might imagine that this would be the speed of the baseball compared to Luke plus the speed of the ship compared to John. That is, you add the speed of the ship to the speed of the baseball. This is just common sense. So, you might think about this as someone riding in a pickup truck past you, and if they throw a baseball from the bed of the pickup truck, you add the speed of the truck to the speed of the baseball when you want to know how fast the ball is moving compared to you. This is just kind of a common sense observation about how one adds velocities. This is we might call it the common sense approach to velocity addition. Okay, so I haven't said anything surprising yet. This is not the paradox that I was going to bring up. But now I'm going to bring up something that's more puzzling. And this is a paradox that arises when considering a slightly different situation. Let's suppose, once again, that Luke is riding in this spaceship. So we've got Luke once again in here. Here's Luke. The spaceship once again is flying at some high speed u past John, who is once again the astronaut watching the ship fly by. Okay, and again there is a glass window on the side of it, so John can see exactly what's going on inside of the ship. But now let's suppose that Luke, instead of a baseball, he has a flashlight. Okay, this is a flashlight, and when he turns on the flashlight, Luke could, in principle at least, measure the speed of the light that's moving away from him. And you probably have heard what the speed of light is. This is something that you learn in grade school. What is the speed of light? Well, I'll draw a little wave here indicating that this is light coming out, and the speed of light is c. What do we mean by c? Well, the speed of light is 3 times 10 to the 8th, or 2.99 and so on, times 10 to the 8th meters per second. That's about 1 foot every nanosecond, by the way. Okay, so according to Luke, the speed of the light beam is just c, right? About 3 times 10 to the 8th meters per second, or 300 million kilometers per second, or the way I like to think about it, 1 foot every nanosecond. Now here is the interesting thing. What is the speed of the beam of light coming out of Luke's flashlight according to John? According to John, well, he also measures the speed of light to be c. According to John, the speed of the light beam is also c. That is 3 times 10 to the 8th meters per second compared to himself. Now, if you find this to be perplexing, then you are thinking about this correctly. Okay? The idea, and what I've just explained, the idea is called the principle of the speed of light. This is the principle of the constancy of the speed of light. You have probably heard this before, that the speed of light is a constant. It is 3 times 10 to the 8th meters per second. You hear this probably since you're little. That's the speed of light. But what Einstein did is he said, this is actually very bizarre if you think carefully about it. It's saying that the speed of light is the same no matter who measures it, and in particular, it's the same whether you are holding a flashlight stationary in your hand or whether you throw the flashlight past you at 1,000 miles per hour. In other words, you don't somehow add the speed of the ship or the speed of the flashlight to the speed of the light itself, like you would have done if you were throwing a baseball from the back of a ship. How is it possible that the speed of light is the same as measured by John and Luke? That is a paradox. That is the fundamental challenge of the theory of relativity. Once you accept, and you don't have to accept this, but once you do accept, as Einstein accepted it, that the speed of light is the same no matter who measures it, it is going to give rise to all kinds of bizarre consequences. Okay? And over the next couple of lectures, what we're going to do is draw out some of those bizarre consequences. Now, let me say a couple of other things before I finish this lecture. One thing I'd like to point out is when you hear that the speed of light is constant, 3 times 10 to the 8th meters per second, it is implicitly assumed that we're talking about in a vacuum. That is, the speed of light is 3 times 10 to the 8th meters per second in a vacuum. It is true that if you shoot a light beam through water or glass, the speed of light is not 3 times 10 to the 8th meters per second. It's somewhat slower. So everything that we're going to be talking about here in the next several lectures, we're going to be assuming that we're dealing with the speed of light in a vacuum. Later on, we're going to do a lab where we measure the speed of light in a fiber optic cable, but we'll come to that issue when we come to it.